Myself, Srijan Banerjee, Assistant Professor, Department of Electrical Engineering of Gargi Memorial Institute of Technology. Today I will discuss about saturation nonlinearity. It is a very common type of nonlinearity. This kind of nonlinearity we can mainly observe in the magnetizing curve of DC motor. In order to understand that phenomenon, in the magnetizing curve of DC motor, we can see the linear behavior initially, but after that there is a saturation in the curve which introduces the nonlinearity in the system. This type of nonlinearity we can also see or we can also observe in an amplifier. In the amplifier, the output is generally proportional to the input for a limited range of values of input. When the input exceeds, then the output will become nonlinear. So this is the basic characteristic curve of the saturation nonlinearity. In the x-axis there will be input parameters and in y-axis there will be output parameters, and we can see here that there will be a linear nature for this characteristic curve initially, and after a certain time there will be a saturations or stability which will occur in the system, and then the system will become nonlinear. So when the system have some linear characteristics, we assume that the slope of that system is k, and after the certain range of input, that is d and minus d, we achieve the stability or we achieve the saturations, and the system will become nonlinear after that range. So if we go for the derivation part, then we assume that the input function xt is equal to omega t, and we assume that the time t1 the input will become d, which we can see in the diagram. For that case, the output of the nonlinearity of that system will become yt is equal to k into xt when the limit will be from 0 to omega t1. Then the output function will become k into d when the limit will become omega t1 to pi minus omega t1. Then we can see that the output yt will become minus k into d, and the limit will become pi minus omega t1 to pi plus omega t1. As we know that for the time t1 input is d, so we can write that d is equal to x sine omega t1, and for that case we can derive that sine omega t1 is equal to d by x. As yt is have odd symmetry, yt is a odd symmetrical function, so according to the Fourier expression we can write the DC component a0 is equal to 0 and the fundamental component an is also 0. So we can say that the fundamental component of yt will be only bn, or rather the first harmonic component is b1. So we can write y1 is equal to b1 sine omega t, where b1 is equal to 1 by pi integration 0 to 2 pi yt sine omega t d omega t. Now if we change the limit from 0 to pi by 2, rather 0 to 2 pi, then the function will become 4 by pi integration 0 to pi by 2 yt into sine omega t d omega t. So this function or this equation also showing the half wave symmetry. So if we break the limit 0 to omega t1 and omega t1 to pi by 2, So we will get two function. So the equation will become 4 by pi integration 0 to omega t1 kx sin square omega t d omega t plus omega t1 integration omega t1 to pi by 2 kd sin omega t d omega t. So is equal to 4 by pi kx divided by 2 into omega t minus sin 2 omega t by 2, and the limit is 0 to omega t1, and plus kd into minus cos omega t, the limit will be pi by 2 to omega t1. After putting the limiting value, we are getting the equation 4 by pi into kx by 2 into omega t1 minus sin omega t1 plus cos omega t1 plus k into d into cos omega t1 to 2 kx by pi sin inverse d by x plus d by x into square root of 1 minus d by x whole square. So therefore y1t, the output equation y1t is equal to p1 sin omega t. So if we put the value of v1, then the function will become 2kx by pi into sin inverse d by x plus d by x into square root of 1 by d by x whole square into sin omega t. As we already get the output equation y1 and we already have the input equation x, so we can easily find out the describing function of the system. We know that the describing function is equal to output equation divided by input equation. By this we can easily find out the magnitude of the describing function, and for the phase angle of the describing function we just consider the function and its angle. So for this case we get that the function of the input and the output equation is sinusoidal wave and the angle is omega t. So as there will be no phase difference between input function and output function, so the phase angle is 0 degree. So if we just put the function, output function and input function, we will get the describing function, magnitude of the describing functions. So for that we just put the value here and we got the describing function, that is 2k by pi into sin inverse d by x plus d by x into square root of 1 minus d by x whole square into sin omega t. So to find out the nature of the system, if we introduce the nonlinear saturation nonlinearity to a plant, then we can easily observe that things by using the MATLAB software. In MATLAB Simulink, we have to draw a block diagram. In the block diagram, we have to take some basic blocks such as source. For this case, we just consider the sinusoidal wave as a source or supply. Then this is a summing block, two channel summing block. Then this is the nonlinear block, saturation nonlinear block. Then there will be the transfer function block, then a multiplexer. This is a 4:1 multiplexer block, and this is the output function, output block or scope. So in this case, as there is a 4-channel multiplexer, that means there will be 4 input and 1 output. Here we consider 4 input and 1 output to observe all the parameters or all the signals of these systems, such as input signal, output signal, error signal and the nonlinear signals. For this case, we can easily observe these 4 type of signals in one output block. So if you draw this block diagram into MATLAB Simulink and run the program, then you can easily observe the characteristics or the nature of the signals from this scope or from this output block. Thank you.